What we've done previously on this course is to just look at what we call the bivariate regression model. In other words, we've looked at the situation where we're trying to explain one variable y by reference to one single explanatory variable x. Now, unfortunately, that framework, whilst we can still answer some questions in finance of interest to us, for example, we could estimate capital asset pricing model one-factor type models, or we could estimate optimal hedge ratios, there are many, many other examples in finance of situations where we need a more flexible framework than that. That being the case, what we want to be able to do is to set up a much more general model where our variable that we're trying to explain y depends on more than one explanatory variable. So suppose, for example, that I was a car manufacturer and I was trying to determine what will be the demand next year for the cars that I produce. There are a number of factors that might influence that demand. For example, the price of cars, the price of transport by bus or train, the price of petrol, the extent to which my car is environment friendly and produces small quantities of gas emissions and so on, might all affect the demand for my cars. Now, what I could do using the framework that we've developed so far would be to estimate separate pairwise regression models where y is the demand for my car, and in the first regression I have the explanatory variable, the price of my car. In the second regression I have the explanatory variable, the price of public transport, and so on. But this isn't really a very satisfactory outcome because we don't want to look at the impact of each of these factors in isolation one at a time on the demand for cars. We want to look at the impact of all of these factors all taken together. So that being the case, we need a more general framework. Similarly, if we wanted to estimate an arbitrage pricing theory type model, then there are likely to be many macroeconomic factors that fundamentally affect stock returns. And that being the case, we need a more general model where we can have many explanatory variables at the same time. So what we're going to do now is to generalize the bivariate regression model that we've developed so far to the multiple regression model, where our variable that we're trying to explain y depends on many, many explanatory variables. In fact, we can have as many explanatory variables as we want, and the notation will generalize very simply. So, just to cut straight to the punchline and explain what the model looks like, we now write the equation yt equals beta 1 plus beta 2x2t plus beta 3x3t and so on, plus beta k xkt plus ut. So now you can see that an equation of this form can have as many explanatory variables in it as we wish. In this case, obviously, we've got a total of k explanatory variables, including a constant. Now, I'm going to come back to that point in a minute. But for now, suffice to say that what we previously called alpha, the intercept term, we now in the more general context call beta 1. And this still represents a kind of intercept term. In other words, it represents the value that y would take if all the explanatory variables took values of 0. And previously, the slope parameter was represented by the letter beta. Well, now we have more than one slope parameter. In fact, in the model that I've just described, we have k minus 1 different slope parameters, which are defined as beta 2, beta 3, and so on up to beta k. Each of these slope parameters represents the kind of marginal impact of changing the explanatory variable associated with that parameter whilst holding all of the other explanatory variables constant. So, for example, beta 2 represents the impact on y of changing x2 whilst holding x3, x4, and so on up to xk all constant. Now, if you look at this equation, you'll see that the explanatory variable numbers start at 2, they don't start at 1. So an obvious question to ask is, why isn't there a 1 represented in that expression there? Why isn't there an x1? Well, the answer is there is implicitly an x1, but we don't actually write it down. Now, just as if we were doing some simple linear algebra and we had x plus 2y equals 3z, so if we were doing some simple linear algebra and we had x plus 2y equals 3z, just as if we had 1x, we wouldn't actually write 1 times x, we'd just write x. Similarly, in this situation, for our multiple regression model, there is an x1, and that x1 is a column of 1s. Now, the purpose of that column of 1s is twofold. First of all, that column of 1s enables us to algebraically represent this situation where we want all the explanatory variables to have a value of 0 so that we can measure the intercept. Secondly, when we use a computer package, we always need one variable multiplied by one parameter each time inside the model. So the computer will see this as beta 1 times x1 plus beta 2 times x2 and so on. So there is implicitly a variable attached to beta 1 called x1, and that variable always takes the value 1 for every observation that we have in the sample. So strictly speaking, we should say that beta 1 is the coefficient attached to the constant term, or we can also call it the intercept term, which previously we called alpha. And x1 is the constant, or the constant variable, although that notation is obviously slightly confusing. So just to give you some other ideas of how we can write this regression model, first of all, we could write the regression model out by writing a separate equation for every observation in our sample. So suppose, for example, that we had a time series regression with capital T observations on each variable. We could write out a separate equation for each point in time, and obviously whilst the values of the y's and the explanatory variables, the x's, are changing through time, the values of the parameters embodying the relationship between those variables always stays the same. An even more useful way to write that model out is to express it in matrix form. And in matrix form, the model is written y equals x beta plus u. Now, the x is a matrix which encompasses all of the explanatory variables together. So in that expression, y will be a t by 1 vector, including all of the observations on the explained variable y. X will be a matrix which will be t by k, representing all of the values on the explanatory variables. So there will be t rows in that matrix, where each row corresponds to all of the observations on all of the variables for each point in time. And there will be k columns in that matrix, where each of the columns represents all of the observations on a given variable. Then beta will be a k by 1 column vector, which includes the values of all of the parameter betas. And finally, u is a t by 1 vector of disturbance terms. So we can see, if we look at that expression, that it's what we call a conformable or legal matrix expression. In other words, if we multiply x times beta, if x is t by k and beta is k by 1, then x times beta will be t by 1. So x times beta has the same dimensions as y and u. So we can see that that's a legal matrix formula. And we can also see that no matter how big the value of t is, and no matter how big the value of k is, that means no matter how big the number of explanatory variables in the regression model we've got is, then the matrix for x and the parameter vector beta can just expand accordingly to fit them. So if we now have a look inside this matrix and see what it contains, then this gives you an example of what y, x, beta and u might look like. So we can see, if we look at the x matrix, in this case, let's suppose that we've only got one true explanatory variable and a constant term in our regression. So in the terminology that I've just used, I said that k represented the number of explanatory variables, including a constant. Now, obviously, you can see that wording is very slightly clumsy, in the sense that if we have a constant, it's strictly speaking, it's not an explanatory variable. But for reasons that will become obvious later on, it's much easier if we stick to this notation. So remember that in the notation I use in the lectures here and also in my book, k denotes the number of explanatory variables including a constant. And that obviously also equals the number of parameters that we have to estimate. Okay, so k is the number of explanatory variables including a constant term, which also equals the number of parameters that we have to estimate. So let's suppose first that k equals 2. So that in a sense goes back to the simple bivariate regression model. And if we look at what's inside the x and beta matrices in this case, then as always the first column in the x matrix will be a column of 1s representing this constant. And this allows us to estimate the intercept term. The second column will obviously be the column of observations on the explanatory variable. Then the beta vector will obviously be 2 by 1 and will include 2 elements, which are the intercept and slope parameters. Now we can see that we can generalize this framework very, very simply. So suppose, for example, that we move to a situation where we had 3 explanatory variables including a constant. In other words, we move to a situation where k equals 3. Then our y equals x beta plus u would now be written in the following way. So y would still be a column of observations on the dependent variable y. X now would look as before, but it would include an extra column for the observations on the third variable x3. So obviously we'd have our column of 1s at the start, then we'd have our column of observations on the second explanatory variable. So these would be denoted x21, x22 and so on down to x2t. So x21, for example, denotes the first time series observation on variable x2. x22 obviously denotes the second time series observation on the variable x2 and so on. If we had k equals 3, we'd have another explanatory variable and therefore another column in this matrix. So we would write that as x31, x32 and so on down to x3t. So you can see that no matter how many explanatory variables we had, all we would simply have to do is continue to add new columns to this matrix. Beta now would include 3 elements because we've got 3 parameters to estimate. So those would obviously be beta 1, beta 2 and beta 3. And similarly as before, the vector of disturbances would be labelled u1, u2 and so on down to ut. So that would be what's inside the matrices in the situation where k equals 3. And we could write that out as a single equation if we wanted to, as yt equals beta 1 plus beta 2 x2t plus beta 3 x3t plus ut. So these are 2 slightly different ways of writing exactly the same regression equation, and both of those are equally valid. And once again, we can generalize those very, very simply and in a very obvious way. Notice once again that the matrices, when we write them in this way, are conformable. This is still obviously going to be a t by 1 vector. This is a t by 1 vector over here. The matrix of explanatory variables is now going to be t by 3 because we've got k equals 3 here. We've got 3 columns in this matrix, and beta is going to be a 3 by 1 vector. So x times beta is t by 3 multiplied by a 3 by 1, which is obviously a t by 1 vector overall. So once again, we've got a conformable or legal matrix equation. Now, an obvious question to ask is, in this more general situation, how do we estimate the parameters and their standard errors? Well, previously we had a set of formulae for the OLS estimators for the parameters and for their standard errors. Now, obviously, we're not going to be able to use those formulae anymore because now we've got more than one slope parameter, and therefore the formulae that we developed before simply aren't general enough to be able to handle that. So what do we do? Well, the framework and the principles that we adopted before still hold here. So previously, we took the residual sum of squares and we minimized that with respect to the parameters alpha and beta. In the matrix notation, we could stack the residuals, the u hats, into a single column, and we could call that vector u hat. In that situation, the residual sum of squares would be given by u hat transposed multiplied by u hat. Now if u hat is t by 1, then u hat transposed multiplied by u hat will be 1 by t multiplied by t by 1, which is obviously a 1 by 1 vector or matrix at the end. In other words, it's a scalar, or it's just got one element. So once again, in this more general framework, when we're minimizing the residual sum of squares, which we now write as u hat transpose u hat, this residual sum of squares will be given by just one number. So there will be one unique model which minimizes the residual sum of squares in each case. To say that differently, there will be one set of parameter estimates, the betas, which minimizes the residual sum of squares. So we still find the model that minimizes the residual sum of squares. The only thing that's different is the set of formula that we need to do that. Now, I'm going to spare you the algebraic derivation of the ordinary least squares estimator in this more general context, but it's in all of the textbooks, and in my textbook it's in the appendix to chapter 3 if you want to look at that. But just to give you the formula, then if we take the X matrix and we construct X transpose X inverse multiplied by X transpose Y, the elements of that thing as a whole, and it turns out to be a k by 1 column vector, that will contain all of the parameter estimates that we require. So, just to reiterate that, there is a single expression, X transpose X inverse multiplied by X transpose Y, which, when we plug the explanatory variables and the values of the explained variable into that formula, we will obtain a set of all of the parameter estimates that minimize the residual sum of squares or best fit that data overall. So once again, we can see that this expression is simply a function of the explanatory variables and the explained variable that we have at our disposal. So it's only a function of quantities which we know. Now, once again, if you want to know where this formula comes from, you can look in a textbook. But all I want to do now is just to go through this formula element by element, just to check that overall it will have the required dimensions. So we said from before that X is a T by K matrix. So if X is a T by K matrix, then X transpose will be K by T. So if X is a T by K matrix, X transposed is going to be a K by T matrix. So if we multiply a K by T matrix by a T by K matrix, obviously overall we get something that's K by K. Now, if we assume for the time being that the inverse of this matrix exists, and in a subsequent lecture we'll talk about some circumstances under which this inverse will not exist, but if we assume for the moment that this inverse exists, then the inverse of X transpose X will also have dimensions K by K. So X transpose X inverse has dimensions K by K. We then multiply that by the matrix X transpose, which remember was a K by T matrix. So once again, if we multiply a K by T matrix by a K by, if we multiply a K by K matrix by a K by T matrix, then we get something that's K by T. Finally, if we multiply that by the vector Y, Y was a T by 1 column vector containing all of the elements on the explained variable Y, and if we multiply the K by T matrix, which is this whole thing here, by the T by 1 vector, then we end up with something that is K by 1 overall. So beta hat is going to be a K by 1 vector which contains all of the estimates that we require. So if we looked at what's inside this, the first element will obviously be beta 1 hat, the intercept estimate. The second estimate will be the slope on for beta 2 hat, and so on, down to beta k hat. And that will obviously be the last element. So once again, we can always use this expression whatever our sets of data are, and this will calculate all of the parameters that we require of our model. So calculating the parameter estimates using this formula is very, very simple. But how do we calculate the standard error estimates? Well, once again, we can't use the same formulae as we had before because they're simply not flexible enough to incorporate all of the slopes. So we need to develop a more general set of formulae that we can use. Now, the first thing that we had to do before, in order to be able to estimate the standard errors, is to get an estimate of sigma squared. That is, to get an estimate of the variance of the disturbances by using the variance of the residuals. Now, previously we used the expression S squared equals sigma u hat t squared divided by t minus 2. In this case, we don't divide by t minus 2, we divide by t minus k. Now, the reason that we divided by t minus 2 previously was that 2 was the number of parameters that we were estimating, or it was the number of degrees of freedom that we lost during the estimation process. In this case, we're estimating k parameters, or we lose k degrees of freedom. So the denominator of S squared is now t minus k. And we can use our matrix notation for the residual sum of squares as being u hat transpose u hat. So S squared now is defined as u hat transpose u hat divided by t minus k. Once we've calculated S squared, then it's very easy to then calculate the standard errors. And we could show that once we've calculated S squared, if we take S squared and multiply it by the matrix X transpose X inverse, then that is known as the variance-covariance matrix of the parameters. Now, we have variances of the parameter estimates on the leading diagonal of that matrix and covariances between the parameter estimates on the off-diagonal elements. Now, obviously, we're not particularly interested in the parameter estimates, so we just ignore the off-diagonal terms. We take the diagonal terms from S squared times X transpose X inverse, and if we take the square root of each of those, then that will give us our estimates that we need of the parameter standard errors. So, to give you an example of how this works, let's suppose that we had a regression model where we've got k equals 3, that is, we're estimating 3 parameters, and we've got 3 explanatory variables including a constant, or 2 true explanatory variables. And let's suppose that somebody has done half of the work for us and has calculated X transpose X inverse and X transpose Y. And let's suppose also that they've calculated the residual sum of squares, which is u hat transpose u hat, and that equals 10.96. And let's suppose that we're asked to calculate the coefficient estimates and their standard errors. So first of all, in order to calculate the coefficient estimates, all we need to do is to take X transpose X inverse and multiply that by X transpose Y. So just to give you a small refresher on how to do these matrix multiplications, although in fact it's very, very easy, we know that beta hat equals X transpose X inverse X transpose Y. And obviously in this case, our X matrices, our X matrix is 2, 3.5, minus 1, 3.5, 1, 6.5, minus 1, 6.5, 4.3. And you can see the usual property of a matrix of this form, that it's symmetrical about the leading diagonal. So for example, the element in the first row and the third column here is the same as the element in the third row and the first column. We then just multiply that by the X transpose Y vector, which was given by minus 3, 2.2, 0.6. So all we need to do in order to perform that multiplication is to multiply along the rows of the first matrices, and of the first matrix and down the column of the second matrix. So the first element up here, and obviously there'll be 1, 2, 3 elements overall. The first element will be 2 times minus 3 plus 3.5 times 2.2 plus minus 1 times 0.6, and that turns out to be 1.1. The second element in here will be given by 3.5 multiplied by minus 3 plus 1 times 2.2 plus 6.5 times 0.6, and that turns out to be minus 4.4. The final element will be given by minus 1 times minus 3 plus 6.5 times 2.2 plus 4.3 times 0.6, and that turns out to be 19.88. So these are our parameter estimates, and obviously these correspond to beta 1 hat, which is the intercept estimate, beta 2 hat, and beta 3 hat are obviously our two slope estimates. So calculating those parameter estimates is very simple. Now, in order to calculate the standard errors, we first need to calculate S squared. And this is going to be given by the residual sum of squares divided by t minus k. Now, the residual sum of squares we know is 10.96. T is the total number of observations, which in this question we're told is 15. And k is the number of parameters that we're estimating, which is 3. So S squared is given by 10.96 divided by 15 minus 3, which is 0.91. We then need to multiply S squared by X transpose X inverse to get the variance-covariance matrix of the parameters. And so the way that we multiply a scalar by a matrix is to multiply every element of the matrix individually by the scalar. So we take our X transpose X inverse matrix and multiply every element of it by 0.91. Once we do that, we have the variance-covariance matrix of the parameters. And the variances of the parameter estimates will be given by the leading diagonal terms. We don't want the parameter variances, on the other hand. We want the parameter standard errors, and we get those by taking the square root of each one. So the standard error estimate for beta 1 hat is 1.35, for beta 2 hat is 0.96, for beta 3 hat it's 1.98. And we use the same kind of notation to write our estimated model as we did in the bivariate regression model case. That is, we write out our estimated equation, and then below each of the parameter estimates in parentheses we put the standard error which corresponds to them. So the standard error for beta 1 hat, for example, 1.35, goes in parentheses below 1.1, and so on and so on. So that's how we estimate the parameters and the standard errors in the multiple regression model context.